Imagine I give you a complicated function like e power x, sin x, or log 1 plus x. How would you calculate its value? For humans, that's difficult. For computers, it's even stranger because computers only know how to do basic operations like addition, subtraction, multiplication, and division. So here's the question. How can a computer calculate complicated functions using only simple arithmetic? The answer is one of the most beautiful ideas in mathematics, the Taylor series. The goal is surprisingly simple. Instead of working with a complicated function directly, we replace it with a polynomial. Why? Because polynomials are easy. They're easy to evaluate, easy to differentiate, easy to integrate, and computers love them. Let's take the function exponential function. At x equals 0, its value is 1. So our first approximation is simply the constant number 1. Not very accurate, but it's a start. Next, we want our approximation to have the same slope as the original function. The slope of ex at 0 is also 1. So we add an x term and get 1 plus x. Now the value and the slope both match. Then we match the curvature. Then the next level of bending. Then the next. Each new term captures another piece of the function's behavior. Every Taylor series follows the same pattern. The function value contributes the constant term. Each derivative contributes another term. Together, they build a polynomial that approximates the original function. In its most general form, the Taylor series is given by this formula. A beautiful idea, turning local information into a global picture. We explored the exponential function. But the same idea works for many others. Trigonometric functions. Logarithms. Different functions produce different polynomials, yet they all follow the same principle. Taylor series. Taylor series turns local information into a global picture. But there's a subtle catch. Not every smooth function is equal to its Taylor series. Some functions have infinitely many derivatives and still cannot be perfectly reconstructed from them. For those functions, the Taylor series is only an approximation, not the whole story. A question for you. Does a function exist independently of its local behavior, or is the function completely encoded in how it changes? What do you think?